Okay. Welcome everybody. Thanks for joining my session about the Java module system. As you know, you can use Slido to ask questions, and at the end of the presentation, I will try to answer them. I am Serban Iordache. I'm a software engineer at Scoop Software in Germany, and my first encounter with the Java module system was a bit more than 1 year ago, when we at Scoop decided to modularize one of our products. We have an open source framework called Copper, which is a workflow engine that allows you to describe your workflows in pure Java. This workflow was Java 8 compatible, and my job was to make it compatible with newer Java releases and to modularize it. At the same time, we wanted that it still works with Java 8, which doesn't know about the Java module system. Since this framework consisted of several libraries, I added a module descriptor to each of these libraries in order to turn them into Java modules. As expected, this was not enough. I also needed to make several changes to our code. But what surprised me was that I also needed a significant amount of work in order to adjust our build process. This was because we used Gradle to build our framework, and at that time, this was March 2018, Gradle had almost no support for the Java module system. That's why I became interested in how to improve things in this area, and for the last year, I contributed to several Gradle plugins for the Java module system, and I also created a few plugins of my own. My goal today is to show you that things have changed a lot in the last year, and nowadays, build tools such as Gradle or Maven allow you to build your modular code with minimal effort. We will look at typical use cases, at things you usually want to do with your modular code, and I'll show you how to automate these things with Gradle or Maven. But before doing this, let's talk about a bit the Java module system. Since Java 9, the JDK is no longer a monolith. It has been split into several modules, and here we can see the module graph of the Java 9 Standard Edition platform. At the top of this picture, there are several modules related to the Enterprise Edition, and because they don't really belong to the Standard Edition platform, they were marked as deprecated in Java 9, and they were removed in Java 11. Now, having code removed from the JDK means that even if you don't modularize your code, even if you don't make any changes to your software, you may still have problems running it on Java 11 or newer versions. And let's illustrate this with a simple program that prints the XML representation of an object. I have here a product class with ID, name, and price, and accessor methods, getters and setters, and also a toString method. Because I want to serialize my class as XML, I also put here a XML root element annotation. My main method creates a new instance of a product. It marshals it, and it prints its XML representation to the output stream. For the sake of completeness, we also have a test unit for our product class. There is not much to test on this class, so I only check if the toString method works as expected. We build everything with Gradle, and here we only specify the test dependencies on JUnit. Let's see how this program works, first with JDK 8. So I execute Gradle run. And the program has printed the XML representation of our product. Now, let's do the same with Java 11. this time it didn't work, and the error message says package Java XML bind annotation does not exist. Why? Because this package is part of the Java XML bind module, which has been removed in Java 11. What can we do in this situation? The code removed from the JDK is still available in public repositories such as Maven Central or JCenter. And I compiled here a list for you with the replacements for the removed modules. In our case, we missed the Java XML bind module, so we will use instead this library, which means that in our Gradle build script, we need to insert this line. So let's put it in our Gradle build script. And let's try to execute again the program. And now it worked. So we saw that we had problems running our code before even trying to modularize it. But we want to modularize our code. And in order to do this, we need to add a module descriptor to our code. A module descriptor contains metadata, such as the module name, the packages exposed by our module, and the module dependencies. We put all this information in a module info Java file, which gets compiled to module info class, which is our module descriptor. So the module info Java contains information about the project dependencies, normal or transitive dependencies, the packages exposed by our module to other modules, the packages open for deep reflection to other modules, the services used by our module, and the services provided by our module, and the implementing class. So the Java module system provides strong encapsulation. A module can specify which parts of it are visible to other modules and which parts of it should be hidden. But sometimes we want to break this encapsulation. We may want to still have access to the hidden parts of a module. And we can do this because the Java-C and Java tools provide us some command line flags. For example, we can specify that a module should export a package that was otherwise hidden. We can specify that a module should require additional modules, or we can specify that a module should open some package for deep reflection to other modules. Before Java 9, we needed to put all our artifacts in the dependency graph on the class path. Now we also have a module path, and this is the location where our modular code should reside, because modules are resolved from the module path. And here are the command line options used by Java-C and Java in order to allow us to configure the module path. Now, depending on the type of an artifact, modular or non-modular, and on its location, on the class path or on the module path, we have 4 possible combinations. Before Java 9, we only had this combination, a non-modular artifact on the class path. Its modular counterpart is having a modular artifact on the module path. But there are 2 other possible combinations. First, having a modular artifact on the class path. What happens in this case? Well, all code on the class path is treated as non-modular, and it becomes part of the so-called unnamed module, for which exports all code on the class path. It reads all other modules, but it is only readable from automatic modules. And what are these automatic modules? Well, they have to do with this combination, having a non-modular artifact on the module path. when we put a non-modular artifact on the module path, it is turned into an automatic module for which a module descriptor is generated on the fly, and this module descriptor requires transitive all other resolved modules. It exports all its packages, and it can read the unnamed module. So automatic modules are some kind of bridge between the modular and the non-modular worlds, because they are the only modules capable of reading code from the class path, from the unnamed module. Let's talk a bit about split packages. A package with the same name is not allowed to appear in two different modules. But sometimes we have the situation where two different artifacts contain the same package. How can we deal with this situation? Javac and Java provide us this patch module command line option, with which we can specify that all classes from a list of artifacts should be merged into a given module. For example, with this command, I say that all classes from this JSR 305 jar should be merged into the JavaX XML WS annotation. Okay, now let's get back to our XML printer program and let's modularize it. We need to add a module descriptor to it, and the module descriptor is quite simple. We saw that we need the Java XML bind module, and we also need to open the package of our application to Java XML bind, because the code in Java XML bind uses reflection in order to analyze our classes and create the XML representation. Now, before trying to execute this modularized code, let's make a small addition to our code. I want to print the name of the module containing our XML printer class. Why do I want to do this? Because we saw that when we put modular code on the class path, it is treated as non-modular. It becomes part of the unnamed module. And in this case, getModule.getName will return null. So this statement allows me to check whether the code has been executed on the class path or on the module path. If it prints null, the code was executed on the class path. And we do the same thing for our unit test in order to see whether the tests have been executed on the class path or on the module path. More than 1 year ago, when I first tried to modularize a Java program, my expectation was that I don't need to make any changes to my Gradle build script. I thought that Gradle has native support for the Java module system, but I quickly found out that this is not true. The good news is that since then, a Gradle plugin for the Java module system was created, and you should use this plugin. But in order to understand what this plugin does, it's interesting to see how to build modular code without it. Let's start by trying to execute this modularized application first without making any change to our Gradle build script. So I will switch to the directory where I already have this modularized version, and let's try to execute Gradle run. And it didn't work. The error message says module not found, Java XML bind. Why? Because by default, Gradle puts all artifacts in the dependency graph on the class path. So we need to explicitly tell Gradle to put these artifacts on the module path. And this is how we do this. I show how to build your modular code without the plugin, because I just want you to show the steps you need to take. So I will not go into every detail of the code appearing on these slides. But what we need to do here is to specify that all artifacts that were previously on the class path should be put on the module path, and the class path should be now only an empty list of files. Let's copy this to our Gradle build script. And now if we try to execute again, we see that the program was executed successfully, but here we say running module null, which means that the code has been executed on the class path. So we also need to tell Gradle how to execute our code on the module path. And again, we say that everything that was on the class path should be put on the module path, and we also add our module to the list of modules to be resolved. So let's also copy this piece of code into our Gradle build script. And now if we execute again our program, we see that it was executed on the module path. We see here the module name. Now let's try to test our program, to execute our tests. The tests were successful, but again they were executed on the class path. So we need to tell Gradle how to compile and execute the test on the module path. Here is a bit more complicated because both the unit test class and the class under test are in the same package. So we need to deal here with a split package between the main module and the test module. And we patch our module, specifying that all classes from the test source set should be merged into our module. Additionally, we need to add the JUnit module to the list of modules to be resolved, and we specify that our module requires the JUnit module. Okay, we copy again this code into our Gradle build script, and this is not enough. We also need to tell Gradle how to execute our tests. It's similar to what we've done for compiling, but here we also need to open our package to the JUnit module, because JUnit uses reflection in order to process the test annotation in our unit test class. And now we copy this code into our Gradle build script, and let's execute again the tests. And we see that this time the tests were executed on the module path. Another thing we may want to do is to create a distribution for our application with start scripts, and we can do this using the install dist task. And now in the install directory we will find our start script. Let's execute it. It worked, but again the program has been executed on the class path. So we also need to tell Gradle how to adjust our start scripts in order to execute the code on the module path. We need to adjust both the bash script and the bat file for Windows. I will not go into detail, as I told you. For me it's important only to show you the steps you need to take. So without further explanations, let's copy this code. And now let's execute again Gradle install dist and start our start script, and this time the code was executed on the module path. As I told you, we have now a plugin that does all these things for us, and this is the Java Modularity module plugin. And all you need to do is to apply this plugin and it's done. So I hope you will appreciate this plugin now that you saw how much work you need to do without it. Okay, let's move on to another use case. Suppose that you have a library that is Java 8 compatible and you want to modularize it. So you want to add a module info Java to this library, but you want that this library still works with Java 8. It's still Java 8 compatible. The problem here is that you cannot compile the module info Java in Java 8 compatibility mode. So what you need to do is first to compile all sources except this module info Java using a value less than or equal 8 for the release option. And then you separately compile module info Java with a value greater than or equal 9 for the release option. And when you do this, you also need to put all classes produced in step 1 to the module path. And finally, you can combine the classes produced in step 1 and 2 into a single jar, and this jar is a modular artifact compatible with Java 8. You can do this with both Maven and Gradle. For Maven, the documentation explains nicely what you need to do, and you also have examples, POM XMLs. So what you need to do is only to read this documentation and adjust your POM XML accordingly. For Gradle is much simpler because we can use again this Java Modularity module plugin, and all we have to do is to call the mixed Java release method with an argument expressing the target Java version for our library. Let's go to another use case. You may want to create a custom runtime image for your modular application, and you can do this using the Jlink tool, which was introduced in Java 9. A custom runtime image is a distribution that contains only the modules required by your application. So it is a smaller distribution than one containing all the modules in the JDK. You can also create your own JRE, your own Java runtime environment with only the modules you need. But Jlink has a strong limitation. It can only work if all artifacts in the dependency graph are modularized. And this is a problem because most of the time your application will have some non-modularized artifacts in the dependency graph. But there are ways to solve these problems, and in order to see how, let's try to create a custom runtime image for a web application based on Vertex. This application serves a page saying hello and a name, and this name is retrieved from the name parameter of the URL, or if this parameter is not available, it will use nameless stranger as default value. The main method initializes the Vertex framework and deploys our vertical. The module descriptor is also simple. We require the Vertex core module and we export our package. We build again everything with Gradle, and this is our Gradle build script. Here we only have this dependency on Vertex core, but Vertex core had its own dependencies. So the dependency graph of our application has actually about 20 artifacts, and almost all these artifacts are not modularized. So here is our problem, how to create a custom runtime image for this application which has many non-modularized artifacts. And we will see in a moment how to do this, but first let's take a look at these lines here. Vertex has netty as one of dependencies, and netty uses the sunmiscunsafe class. This class provides low-level mechanisms, and it was designed to be used only by the core Java libraries. It is JDK internal API, so it should not be used outside the JDK, but because it provides critical functionality that it is very difficult or even impossible to be implemented otherwise, it is used by several libraries, and netty is one of them. The problem is that sunmiscunsafe is no longer part of the standard edition platform. It was moved into this JDK unsupported module. So in order to let our code still work, we need to add the JDK unsupported module to the list of modules to be resolved, and we also need to specify that netty common requires this JDK unsupported module. Okay, let's get back to our problem, how to modularize this application. Luckily, there is a tool called Moditect that helps us generating a module descriptor for each of the non-modular artifacts, and it adds it to the artifact. So what Moditect does is to modularize each of our non-modular artifacts. And Moditect provides plugins for both Maven and Gradle. Let's see how the POM XML for our Vertex web application would look like. We need to use the Moditect Maven plugin, and then for each non-modular artifact in our dependency graph, we need to configure its module descriptor. Most of the time, the only thing we need to do is to provide a name for this module, because the plugin is able to figure out what to put in the module descriptor. That's because it uses JDEPS. JDEPS is a tool for analyzing dependencies. It was introduced in Java 9, and it can generate a module descriptor for you. However, sometimes JDEPS is not able to generate the correct module descriptor for an artifact. And in such cases, Moditect allows us to provide explicitly the module descriptor for an artifact, such as here or here. Moditect also allows us to configure the module descriptor for an artifact using wildcards. So here, for example, I configure the directives of our module descriptor, such as requires, exports, uses, and so on, using artifacts. I specify that for this module, I want to export all its packages except those containing impl in their name. With Gradle, you need to do something similar. We apply the Moditect Gradle plugin, and then again, for each artifact, we need to configure its module descriptor. And again, if JDEPS is not able to generate the correct module descriptor, we can provide it explicitly. The approach taken by Moditect is a very clean one. We just modularize each of our artifacts. If we have a complex application, we may have about 100 artifacts in our dependency graph, and if most of them are not modularized, we will need to configure a lot of module descriptors here in our Gradle build script or in our POM XML. And if you're lazy and you think this is too much work to do, you can take another approach, the so-called badass approach. In this approach, we combine all non-modular artifacts into a single one, into a so-called merge module. And then we only need to modularize this merge module. And there is a Gradle plugin that does exactly this for us. And this is how we use the plugin. We apply it, and then the plugin provides us a Jlink extension where we can specify options for the Jlink tool, and we can also configure our merge module. Most of the time it is not necessary to explicitly configure the merge module because the plugin will figure out what to put in this module descriptor. But sometimes it may miss some information. For example, in the case of our Vertex web application, the plugin is not able to detect all the services used by our application, so we need to provide them here explicitly. Okay, let's see how to create a custom runtime image for our Vertex application. The plugin provides a task called Jlink, so we'll execute this task and it will create the custom runtime image of our application into a directory called image. We also have a task called Jlink zip, which will create a zip of our image, and we can see it here. So the zipped custom runtime image of our application has 32 megabytes, and in this directory we have our image. Let's see what's there. So this image contains several directories. The most interesting are the bin and the lib directory. Let's see what's in the bin directory. We see a lot of DLLs here because I'm on Windows here. We also have the Java executable in this bin directory, and we also have a shell script and a bat file for starting our application. So let's try to start it. And now if I open localhost 8080, I see this hello nameless stranger, or I can also provide a name parameter and then it says hello GeeCON. Now let's look what is in this lib directory. Here we see a big file which is 25 megabytes big. This file contains all the classes needed by our application, both from the artifacts in our dependency graph and also from the JDK. We can see what's in this file using the JImage tool, which is part of the JDK. So I'll say JImage list modules, and it prints all the classes in this file. I will stop it yet, and let's grep for the module names. And we see that this file only contains the modules required by our application. We don't have here all the modules available in the JDK, only those required by our application, and that's why this custom runtime image is smaller. Okay, now let's go further to another use case. Especially when you have an application with a graphical user interface, you may want to create an installer for this application. And this is possible using the JPackage tool introduced in Java 13. This tool is based on an older tool called JavaPackager, which was available in JavaFX, but it was removed in Java 11. And the badass Jlink plugin, which we just saw, also provides a task for allowing us to create platform-specific installers for our programs. Let's see how it works with a small JavaFX application that displays a label saying "Hello GeeCON." This is the module descriptor of our application. We need the JavaFX controls modules, and we also need to open the package of our application to JavaFX graphics, because this launch method here uses reflection in order to create an instance of the application class. This is the Gradle script that allows us to create an installer for our application. There are two interesting things here. First, we use this JavaFX plugin, which takes care of providing the required JavaFX libraries for our platform. And it allows us to specify the JavaFX modules needed by our application, putting them in this JavaFX block. The next thing is that we can provide additional options to our JPackage tool. For this simple JavaFX application, we don't need to provide any options. So I put this code here only to show you how you can do this such a thing. For example, to show you how you can add specific options for the Windows platform. We say here that we want a per user installation, and that the user should be able to choose the directory where the application will be installed. But again, we don't need this code for our application. We can throw away this piece of code, and the plugin will still create the right installer for your application. Let's see how it works. We have a task called JPackage, and we execute it. When we create a custom runtime image for an application, we can create different custom runtime images for different platforms, and the Jlink tool allows us to create custom runtime images for different platforms on the same machine. So I'm here on Windows, but I can create custom runtime images also for Linux or for Mac. All I need to do is to provide the location of the JDK distribution for the specific platform. And the Gradle plugin, the badass Jlink plugin, has support for this. You can very easily create custom runtime images for all platforms. With JPackage, this is not possible. If I want to create an installer for Linux, I need to execute JPackage on a Linux machine. If I want it for a Mac, I need to execute JPackage on a Mac. Here we are on Windows, so the JPackage task has created for me an installer for Windows. And this is it. Let's execute it. And now it installs our simple JavaFX application. It's done, and now we can try to start this application, and we see here, hello GeeCON. The last use case I want to show you is how to create a custom runtime image for a non-modular application. Sometimes it may be very difficult to modularize an application, and you may decide to not modularize it. But maybe you still want to create a custom runtime image for this application. And what you actually do in this case is to create a custom JRE containing only the modules required by the application, and then you copy all the classes and dependencies of your application along with the task scripts into the directory of this custom Java runtime environment. And again, there is a plugin that allows you to do this, and this is how you use it. You apply the plugin, and then it provides a runtime extension where you can configure options for the Jlink tool, and you can also specify the list of modules required by your application. Most of the time you don't need to specify these modules because the plugin is able to figure out which modules are required by your application. But in the case of our Vertex web application, this was not possible due to this JDK unsupported module, which contained some misconcept. The plugin was not able to detect that we need this module, so I had to explicitly specify here the list of modules to use. So we saw in this talk how you can build, test, run, and create scripts for your modular application, how you can create a modular artifact that still works with Java 8 or older versions. We saw how to create a custom runtime image for a modular application, even if this application has non-modular artifacts. And we can do this with ModDetect, which modularizes each of our non-modular artifacts, or with a badass Jlink plugin, which creates a single merged module. We also saw how to create platform-specific application installers, again with this badass Jlink plugin, which uses the JPackage tool, and how to create custom runtime images even for non-modular applications. And we also saw this JavaFX Gradle plugin, which is useful when using JavaFX. For Maven, the ModDetect plugin is very useful. You can use this plugin in many situations. So let's see if there are some questions. Do you think is it possible to modularize Spring Boot web application? For now, Spring 5 is not modularized. I tried to modularize the Spring Pet Clinic, and it worked, but it wasn't nice. I can show you. I can show you how the Gradle build script for this application looks like, and you can decide if this is a nice Gradle build script or not. So I needed to do many things. First, I needed to manually configure the merge module because there are many things that didn't work automatically. And then I also needed to make some not really elegant changes. For example, Spring scans the class path in order to do its magic. And when we have a modular application, the class path is empty. So in order to let Spring see the classes in the class path, I needed to put to put the classes on the class path. That's what I do here. So I copy all the classes on a here is what I did it. I copy all these classes on a specific directory and put this directory on the class path in order for Spring to be able to find it. As you see, I gave this directory a strange name because these classes will not be used, will not be loaded by a class loader. They are only needed by the class path scanner of Spring. I didn't try to do something similar with Spring Boot. I expect that this will also be complicated. So it's probably not a good idea to try to modularize a Spring Boot application right now. But I didn't try it. Okay, what tool did you use to switch Java version? It's not a tool, I just wrote a script to do this. Will module path and class path coexist forever? I think yes. I don't know for sure, but I assume they will coexist forever because not every application and library will be modularized. I expect that even in 10 years, many applications and libraries will be not modularized. So module path and class path will coexist. That's my opinion. Okay, it seems there are no other questions, so thank you.